Welcome back to my series of solving project Euler problems with simple Python programs, and hopefully I am able to convey some mathematics or programming information on the way. Today we are at problem number 9, which is about Pythagorean triplets. As the Greek name may suggest, we are again in ancient math territory. A Pythagorean triplet is defined as described in the problem, but I like to think of it as right-angled triangles built from toothpicks. The three numbers represent the number of toothpicks you need for each side in that triangle. The smallest Pythagorean triplet is 3, 4, 5. So with 3 toothpicks on one side, 4 on the other, and 5 in the diagonal, you get the perfect right triangle. I will create one so that you can see such a construction. If you were to try the same thing with 1, 2, and 3, you would not be able to build a triangle with a right angle, so that is not the Pythagorean triplet. In mathematics, you can say the same thing by saying that there are 3 integers, a, b, and c, where a squared plus b squared is c squared. The problem here claims that there is such a Pythagorean triplet, or a right triangle built from toothpicks, in this case 1,000 toothpicks, and asks us what triangle that would be. We can calculate this in several ways, but I will start with the obvious brute force method. Let us try different sides, A and B, and use the remaining toothpicks for the diagonal. If it works, we have our answer. We do need to be careful here so that we check that the diagonal has no gaps or overlaps. This is where you can accidentally get things wrong in a computer program. You might try to calculate the diagonal backward through the Pythagorean formula and the square root, and then see if it is a whole number, an integer. But such checks are hard to get right, since computers are a bit approximate for decimal numbers. A computer may claim a number is exactly 1000 when it should have been 1000.000001, and then you will respond with something that is not correct. So I'm doing all calculations with integers, which is something that computers can do without losing precision. If the numbers match up, then we have a solution. Let us create a function calculate ABC that returns the a, b, and c we find. And the function will take the number of toothpicks, or well, the sum of a and b and c as an argument. First run I will use the example with a plus b plus c equal to 12. Let us loop from 1 to the number of toothpicks as side A. For every such choice, we'll try all variations of toothpicks for side B by looping from A to target. Finally, we allocate the remaining toothpicks to the diagonal C and check if these numbers make a Pythagorean triplet. If yes, then we can return these numbers. Also, we should add an assert in case there is no possible solution. The problem text claimed that there was one, but who knows. Let us run this and see what it tells us. I will start with the example. A triangle with a circumference of 12 toothpicks. It gave us the expected answer, 3, 4, and 5. So time to go for the real problem, 1,000 toothpicks. We have a solution, and it took us only 40 milliseconds to get it. 200, 375, and 425 toothpicks on the different sides. More than I can create a model of. Time to go a bit deeper into the math to get the more optimal solution. Already the ancient Greeks realized that the sides A and B and C are not independent. If you change one, you have to change the other two as well. And for some A and B, you might not be able to get your toothpicks into the diagonal unless you cut one off, or add a bunch extras. So Euclid realized that you can actually work with just two numbers, and using those you can get all A, B, and C that will work. Often these numbers are called m and n. So you pick one m, and you pick one n, and you have a triangle. One side will be m squared minus n squared toothpicks. The other side will be 2 times m times n toothpicks. and the diagonal will be m squared plus n squared toothpicks. I'll try to insert the total number of toothpicks into these formulas and see what we get. This might take a while unless I cut it out. So, I have a formula here. And using this formula, I can see that the total number of toothpicks will be 2m squared plus 2 times m times n. And we know that the total number of toothpicks is 1000, or in case of the example, 12. So if we know m, we can calculate n directly. The number n turns out to be the total number of toothpicks divided by 2m minus m. We can just pick an m and see if it works. So trying one m at a time, calculating n. If n becomes negative or larger than m, then it's not correct since n should be between 0 and m. I also need to round n to an integer, and again we're into dangerous territory. So going back to integer math and checking that everything works out. If it does work out, then we have our solution. And we just need to calculate the sides a, b, and c from m and n using the formulas I mentioned a minute ago. So let's run the new program. And we have our solution. Same as before, 200 toothpicks on one side, 375 on the other side, and the remaining 425 toothpicks for the diagonal. And this time the calculation took no measurable time, so this was much more efficient. Except that it took much longer to code, and it is code that is much easier to get wrong. We'll come back next time for more Project Euler, and please like and subscribe.